This video will explain the difference between mass and weight. So to get things started, let's look at some objects that we might want to compare. Suppose we had a pile of feathers and a pile of nails. And I put them both on a balance and I had 1 kilogram of each one. What does it mean to say I have 1 kilogram of feathers and 1 kilogram of nails? The pile of feathers is going to be much larger than the pile of nails, but they're both 1 kilogram. Okay, well, here's what it means. If the mass of both piles is 1 kilogram, then both piles contain the same amount of matter. If we want to get down to it, what it means is both piles have the same number of protons, electrons, and neutrons. We don't have to worry about that necessarily, but we can say they both have the same amount of matter. So, when we talk about mass, mass is the quantity that tells us how much stuff or matter we have. Okay, why do we care about mass? Well, it's a really useful thing to know. It's so useful that we give it a special name. Mass is what we call a fundamental property of objects. That means that it's one of the things that we can use to describe that object. And no matter where we go, that fundamental property is always going to be the same. It's not something that changes. That's why it's useful to describe the object. So if I say I have a kilogram of feathers in the classroom, and I take that same pile of feathers and I go to the top of Mount Everest, I'm still going to have a kilogram of feathers. It's the same amount of feathers, it's the same amount of matter. Mass does not change if we move to a new location. Weight is different. Weight is not the same as mass. Okay, they're related to each other, and I guess we're going to have to figure out how, but they're not the same. Things have weight because they're being pulled by other things. On the Earth, it's the Earth that causes us to have weight. If we could get far away from the Earth, out in the middle of space, away from everything, we would be weightless. So because we're close to the Earth, we have weight on the Earth, and we know how to calculate how much weight we have on the Earth. The interesting thing is, if we were to go to the moon, we would have a different weight than we have on the Earth, because the moon is different than the Earth. So if it's the moon pulling me, I'm probably going to weigh less, because there's less of the moon to pull. The Earth, with a lot more mass, has a larger pull, so I weigh more. So it'd be really awesome if we could all go to the moon to figure out what our weight was. But that's not very practical. So we need another way to do this. Right? Through lots of experimentation, we have found that weight and mass are directly related. And when we say weight, what we really mean is the force exerted by gravity, the force that the Earth uses to pull on us when we're here close to the Earth. All right? The force and mass are directly related. So those words directly related tell me how to make a graph. If I were to graph force and mass, force would be the dV, mass would be the IV. This is what it would look like. I put two lines on the graph, one for the Earth and one for the moon. Directly related means that these lines are straight. When I increase the mass of something, its weight will also increase. That's why we have straight lines. Now, if we want to calculate the weight of something, we can write the equation of this straight line. Notice both lines go through the origin. So that means when I write my equation, there's going to be no y-intercept for the equation of my line. And here's what it looks like. My dependent variable is my force. That's my y value. My independent variable is my m. That's my x value. And so I have y equals a number, a slope, times x. That's the equation of a straight line. The slope value for these graphs, we assign the letter G to. You've seen this little g before, and in fact, you probably know that little g on the Earth is 9.8 meters per second squared. We can verify that by doing this experiment. If we measure the weight for different masses, we should find that the ratio of weight divided by mass equals 9.8. All right? So let's sum all this stuff up. Mass tells us how much matter we have. Force is a pull. Weight is a force, so weight is a pull. Weight and mass are different things. Mass is constant. No matter where I go, I'm always going to have the same mass, the same amount of me. But if I go to different places and have different poles, then I'm going to have different weights. On the moon, I weigh about 1/6 as much as I do on Earth because the moon is so much smaller in mass. If I could go to Mars, I'd weigh about 1/3 of what I weigh on the Earth. Mars is bigger than the moon, but still smaller than the Earth. Okay? We want to calculate the weight of something. We multiply its mass in kilograms times the value of g in meters divided by seconds squared, and the answer that we get is the amount of weight in newtons. I hope this video helps you sort out mass and weight.